In the 1960s, a group of researchers, including some of the best minds in physics at the time, were working on something that Einstein would have disliked. Einstein's greatest legacy is the theory of general relativity, a set of 10 equations that tell us exactly how matter, energy, space and time relate to one another. One of the key pieces of his theory is that we learn that time is just like any other dimension, and what we think of as time, immutable, ticking clocks, are in fact merely grid lines that we impose on a four-dimensional universe. It was clear almost from the beginning, however, that time is not the same as space, and in physics, time had always been treated differently. Quantum mechanics in particular talked about position and time very differently, and could not easily reconcile treating them similarly. This group of researchers was interested in understanding how his theory of general relativity could be turned into a theory more like the mechanics of the past. A theory where space and time were not quite so interlocked, but rather where space could be described as evolving in time. They called it geometrodynamics, the dynamics of space evolving in time. One of the outcomes of this program was a description of general relativity using a little-used approach to classical mechanics. With it, they created an equation that, although proved to be equivalent to general relativity in 1969, was nevertheless timeless. It was not timeless in the sense that it treated time like any other coordinate. It didn't describe space evolving in time at all. To understand what they did, we have to go back in time. In the 17th and 18th centuries, there was a raging debate over the nature of light. Was it made of particles or was it purely a wave? We know that by the 20th century, thanks to quantum mechanics, the answer would come that it was both. But for that to happen at all, a different form of classical mechanics had to come first. In 1680, Dutch polymath Christian Huygens discovered an intimate relationship between rays of light and their wavefronts. If wavelengths are small, they turned out to be equivalent. You can deduce one from the other. In the case of a burst of light traveling through empty space, the ray of light travels in a straight line from its source, while the wavefront is a growing sphere. That is an obvious case, but even in non-obvious cases where the source of light is an irregular line or surface, and the light travels through irregular media, like water and air, the principle still applies. Wavefronts and rays are equivalent ways to look at light, but also all mechanics from water to rockets. Although by the late 16th century, Newton had already introduced his laws of motion, it would be another 100 years before Lagrange would turn this into a general theory of motion for all matter. This general theory was based on the principle of least action. In the case of rigid objects like balls and rockets, the action is simply the kinetic minus the potential energy. In the case of optics, it is the traversal time. In each case, the action is minimal. This approach turned out to be equivalent to energy conservation, which provides equations for motion called Hamilton's equations. For balls and rockets, the energy is kinetic plus potential energy, and that remains constant. For optics, it is related to Snell's law, which governs the angle of refraction as a light ray passes from one medium to another. These two approaches are also equivalent to a third approach, the wavefront approach, also called the Hamilton-Jacobi equation. This approach relates the action to the energy so that you can compute the wavefront of anything from free particles to light to fields. A free particle travels in a straight line, but also has a spherical wavefront. Of course, if you have only one particle, you can't imagine how this would form a spherical wavefront, but each particle has an initial momentum that determines what direction it goes. The wavefront accounts for all initial momenta. You then have to nail down your particle using final conditions to know where it will end up. From this formulation of mechanics, physicists in the 1920s came up with the wave description of quantum mechanics. While the classical particle has a definite initial momentum and final position, the quantum particle only has one when it is measured. Before that, it is the entire wavefront. To account for this, we have the Schrödinger equation, which developed from the Hamilton-Jacobi equation. In the case of general relativity, researchers in the 1960s developed the three classical mechanics equations for geometrodynamics, while the least action principle was developed by Einstein and Hilbert for the 4D version of the theory. Another least action principle was needed for the evolution of 3D space in time. This led to the energy conservation or Hamiltonian equations, first by Paul Dirac and then the more popular ADM formalism. Finally, the Hamilton-Jacobi-Einstein equation was written down in 1962. In both the least action and Hamiltonian versions, time appears as an explicit parameter. You're expected to choose how you want time to be measured. In the wavefront version, however, no such choice needs to be made. The wavefront approach is instead more concerned with how the wavefronts change with respect to changes in spatial geometry. In other words, for a small change in the curvature of space, how does the shape of the wavefront change? In this sense, the wavefront approach is parameterized not by time or even position coordinates, but by the infinite dimensional quantity of geometry itself, the total collection of points in space, not just one. But wavefronts in what? It can't be space because we are talking about wavefronts of space, not in space. Unlike particles, which have wavefronts that are spread over space and propagate in time, Einstein's theory has wavefronts that spread in an infinite dimensional superspace where every point defines a spatial geometry. Individual rays or paths through superspace are defined not by how they change in time, but in an infinite dimensional parameter. This parameter helps to define what it means for two geometries to be near one another on a trajectory, in the same way that time helps define what it means for two positions to be near one another for a particle trajectory, but it is a bit artificial. It doesn't correspond to anything real. There is a way, of course, to get back to the ordinary Einstein equations, but it is worth questioning whether we can, by contemplating the Hamilton-Jacobi-Einstein equation, learn to think timelessly, like the heptapods in the movie Arrival. In a sense, can we, by learning the language of space, matter and time, grok that time itself is not the linear progression we experience, but an artificial parameter? If we can imagine the universe not as something that linearly evolves in time, but as a wavefront propagating within an infinite dimensional superspace, time is less meaningful than the mere concept of difference. When a spatial geometry varies, it moves from one point in the superspace to a nearby one. How spatial geometries propagate from one infinite dimensional wavefront to the next comes from the HJE equation. Yet that propagation itself need not be glued to a concept of time or any parameter. If we take this idea to the quantum realm, we end up with an equation called the Wheeler-DeWitt equation, which generalizes all this. The Wheeler-DeWitt is also, like the HJE, but unlike the Schrödinger equation, timeless. It is not a complete theory of quantum gravity because it lacks completion, but it does tell us what quantum gravity ought to look like. This is considered a problem in physics because we cannot account for time in quantum gravity. But perhaps the problem is that time isn't what we think it is. Maybe, just maybe, time is an emergent phenomenon, a construct of our limited perception, and the true nature of the universe lies in the timeless interplay of geometries in an infinite dimensional space. In Kurt Vonnegut's classic novel Slaughterhouse-Five, the main character, Billy Pilgrim, becomes unstuck in time. Arrival, based on a short story by the great Ted Chiang, clearly borrowed a lot of the elements of this novel as well. Billy discovers that he experiences his life out of order, and moreover, there is nothing he can do to affect what happens. His life is fixed, his future determined. Yet the Wheeler-DeWitt equation and its classical approximation, the Hamilton-Jacobi-Einstein HJE equation, tell us that this is not true. The endpoint of our journey is not fixed until it is observed or measured. Rather, our lives are wavefronts expanding into the space of all possibilities. If we were able to perceive the future, then it would become fixed. But as long as we don't know what is going to happen, the future may be undetermined. Moreover, time itself is unobservable. All we can observe is change. The reason we can't observe time in the Wheeler-DeWitt equation is because, in general relativity, time is not fixed for all observers. Those who dwell on different paths through superspace, and even those on the same path, may have entirely different experiences of time. By analogy, in quantum mechanics, the concept of a particle trajectory no longer has meaning because it has been smeared out across space. In the same way, in quantum gravity, the concept of time no longer has meaning because it has been smeared out. From a quantum perspective, your experience of time is an illusion created by the constructive interference of waves in superspace. Constructive interference is when, for example, two light sources interact and create a stronger beam of light. Because light is made up of waves, the interaction creates alternating light and dark bars. The light ones are constructive and the dark ones are destructive. The same occurs for superspace geometries. As the waves of the geometries interact, they can be constructive or destructive. Only the constructive ones contribute to the classical history that we call spacetime. Which geometries will constructively interfere in the Wheeler-DeWitt equation is not determined. We cannot, therefore, become unstuck in time like Billy Pilgrim, because the future is not fixed. Time itself is not fixed. To say that at time t in the future X will happen is rather a kind of sleight of hand. We are looking at the future as if it were already the past. If we are talking about the orbits of planets, our prediction may be quite reliable because the probability is high, but for our chaotic lives on Earth, such predictions are not so reliable. To be truly unstuck in time, we have to perceive time at the quantum level, as a smeared-out wave expanding into a space of possibilities, each with a probability that it will happen, with no ticking clock indicating when those possibilities occur. The position of those hands is instead a smeared-out probability field, like the position of an electron around an atom. Our past does not determine our future. Where we will end up is somewhere on the wavefront, not at a time, but at a configuration of reality. This is why the multiverse interpretation is so important, even if that is not what really happens. We have many potential timelines stretching out before us. Whether all of them happen or only one from our current state in time, they are all equally real. A good example of this kind of perception of time is from one of my favorite movies of all time, starring Jared Leto. In this movie, the main character becomes unstuck in time, but unlike in the Vonnegut novel, we quickly find out that he is experiencing multiple mutually exclusive timelines. Likewise, you and I, to become unstuck in time, must perceive the future in this way. Although we may not have as much control over our futures as we would like, in fact, randomness plays a greater role. Nevertheless, our future is determined at least partly by our choices. To be unstuck in time is to perceive all those possible futures stemming not only from our own choices, but from unanticipated events. For example, a great proportion of my life was determined by randomly placing my resume on a website without any expectation that anything would happen. That random act led to my now 10 years at Georgia Tech. This shows that the future can be wilder and more unknowable than we can even imagine. But to perceive the future, we have to expand our imaginations. If we only ever expect the ordinary to occur, or we let ourselves fall into despair that nothing will ever change, that is a fault, not in our lives, but in our imaginations. Our imaginations are future perceiving muscles, and like any muscle, we have to exercise them to imagine the limitless possibilities, whether they may come to pass or not. So, as we conclude this journey into the quantum dance of time, remember that the future is a vast, uncharted territory. Let your imagination be the compass that guides you through the infinite potential of time.